हेलो गाइस, वेलकम यू ऑल फॉर टुडेज क्लास। आज हम गोइंग टू स्टार्ट न्यू टॉपिक दैट इज applied thermodynamics. It is a application of thermodynamics in various engineering processes, power generation, power plant, and so many processes in which heat transfer involved, heat pump. There are so many applications of engineering thermodynamics. That's why it is called steam applied thermodynamics and gas turbines and steam turbines, working of steam engine, all this work on the basis of the applied thermodynamics. So here we are going to derive some equations. So starting from the Maxwell equations, we will derive Maxwell equations and then Clausius-Clapeyron equation, Joule-Thomson coefficient, Joule-Thomson, Joule-Kelvin expansion. And before starting to Maxwell relations, we first discuss some mathematical relations, differential equations, partial and exact differential equations, which are applied in Maxwell equations. And Maxwell equation is a combination of the thermodynamic potential. Thermodynamic potential is a combination of thermodynamic properties which are very essential to define various tedious equations and Joule Kelvin expansion coefficient and Clausius-Clapeyron equation, and so many applications are there of Maxwell relations and tedious equations. So before starting Maxwell relations, we will first discuss what are differential equations which are required to correlate these relations with Maxwell relations. So we know that some thermodynamic functions, some properties, because in thermodynamic system we have to define temperature and pressure and volume. Thermodynamic system can be defined by three properties. These are temperature, pressure and volume. And out of these three properties, two are independent and one is dependent. So how one property can be correlated with the next of two properties? This is I will discuss here with the help of the mathematical differential equation, exact and partial differential equation. Then we correlate these x, y, z. Suppose function is here. We take suppose f x, y, z. This is a function. This is a function f x, y. X, y, z are properties, and these x, y, z properties we can x equal to p and y can be as t and z can be taken as v. Pressure, temperature and volume. Later we take these x, y, z into pressure, temperature and volume. Starting from this function x, y and z. So one property, x can be defined in terms of y, z and y can be defined in terms of x, z. First we define x. X is a function of yz. X is a function of yz. We can differentiate dx, take a exact differential dx equal to, by using mathematical properties. So dx equal to del x by del y at constant z dy and plus del x by del z at constant y dz. This is equation number 1. Again we can define x, y in terms of function of x and z, y as function of x and z. So take differential equation dy equal to del y over del x, del y over del x at constant z dx plus del y over del z at constant x dz. This is equation number 2. This is equation number 2. So now putting value of dy in equation number 1. Putting value of dy in equation number 1. So dx equal to, here take value of dy in equation number 1. So dx equal to del x over del y at constant z and dy, putting whole value of dy equal to, this is del y over del x, del y over del x at constant z, del y over del z at constant x dz and plus del y over del z at constant x. So now multiplying with del x multiplying this equation with del x. So you will get, so dx equal to del x over del y, del x over del y at constant z, and del y over del x at constant z, and plus del x by del y at constant z, and del y over del z at constant x dz, and plus del y over del z, del y over del z at constant x dz. So now erasing this one, solving this equation, again we writing here dx equal to left side, dx equal to del x over del y at constant z, del y over del x at constant z dx, and plus here plus, taking dz common, del x over del y at constant z, del y over del z at constant x, plus del y over del z at constant x. This is a dz. Taking dz out, because you can see here dz and here dz. So taking dz out. Now you see this equation, dx equal to, see this equation. This is possible only when this term equal to 1 and this term becomes 0. You see that dx equal to del x over del y at constant z, del y over del x at constant z dx. Here dx, here dx. This is possible only when this term becomes equal to 1 and this term becomes 0. But see that this is a, so this equation is possible only when, because dx here and dx here, and here dz, this term whole term becomes 0 and this term becomes 1. Then this equation dx equal to dx. So now putting this one equal to 0. See here this term becomes 0, sorry 1. This equation is, here you see dx and here you see dx. If it's possible when this term equal to 1 and this term becomes 0. Putting del x over del y at constant z, and del y over del x at constant z dx. This equal to 1. So del y over del x at constant z equal to 1 upon del x upon del y at constant z. So this is equation. This equation is known as a reciprocal relationship. A reciprocal relation. This relation will be used in derivation, further derivation of other TDS equations, and Cp minus Cv equal to R. All these equations, this is very important relations. You will see that del over del x at constant z equal to 1 upon del x upon del y at constant z. This equation is known as reciprocal relationship. Now see second equation. Second term, this term, because this term equal to 0, this term should be 0, that's why dx equal to dx. So taking second part, del x over del y at constant z, del y over del x at del y over del x. Taking second part, del x over del y at constant z, del y over del z at constant x, plus del y over del z at constant x equal to 0. So here by taking this term right, so del x over del y at constant z, and del y over del z at constant x equal to minus del y over del z at constant x. Using reciprocal relationship, del x over del y at constant z, del y over del z at constant x, and del z over del y at equal to minus 1. So this term, taking this term left side, dividing this term by this term, so and using a reciprocal relationship, you get this equation, and this equation known as a cyclic relationship. Cyclic equation among cyclic equation for three parameters x, y, z, x, y, z. This function equal to 0. So you can see here del x over del y at constant z and del y over del z at constant x into del z over del x at constant y equal to minus 1. So this equation will be used when we convert x, y, z. Suppose here we take PVT, P, V and T. In this equation, we can write cyclic equation taking del P over del V at constant T, del V over del P, del V over del P, del T at constant P and del T over del P at constant V equal to minus 1. So this is a cyclic relation among three. We have taken x, y, z. We have related cyclic relationship for the parameters x, y, z, and by using analogy, we correlated by pressure, volume, and temperature. This equation del P over del V at constant T into del V over del T at constant P into del T over del P at constant V equal to minus 1. These two relations are very useful for the derivation of the Maxwell relations. So now we use going to second page. Let another parameter be defined here. Let z is a function of x and y. So dz is equal to del z over del x at constant y dx plus del z over del y at constant x. If it is a partial differential equation relating with the exact differential equation dz. Now considering this quantity equal to m and this one equal to n. So this equation simply break into dz equal to m dx plus n dy. M dx into n dy. Now let define m. M equal to del z upon del x at constant y and n equal to del z over del y at constant x. So here let us define del m over del y at constant x equal to del upon del z, del upon del y and del z upon del x equal to del square z upon del y del x. Similarly, we can define del n upon del x at constant y equal to del upon del x and del z upon del y at constant x equal to del square z upon del x del y. So here you can see from this relationship you can see del m over del y at constant x equal to del n over del x at constant y. So this relation we will use for derivation of the Maxwell relation. This equation we can use for the derivation of all Maxwell relations. So I think today in next this is sufficient for today's discussion. By this relation we can use for the derivation of the Maxwell relations, and Maxwell relations we will derive for the relationship of internal energy function, Gibbs energy function, Helmholtz energy function, and enthalpy. So we define internal energy function U in terms of temperature, volume, and entropy. Gibbs energy function G in terms of temperature, volume, and entropy, and enthalpy in terms of temperature, volume, and entropy, and Helmholtz function. In next class we will derive equations for Maxwell relation. These are very important from competition point of view and for derivation of other equations. Thank you very much.